Okay, so a lot of you are expressing extreme dismay over this particular problem. If you want to do B, then you're going to have to answer. You're going to really rely off your free body diagram here. So in the beginning here, they're at rest. All right, and the other guy says that wrote it. No, he's just suspended, so everything's just in static equilibrium. So at that moment, you have, let's see, well, person A has his or her weight, MAG, acting downward. We bring you in a little closer, maybe. There we go. So it's got MAG acting downward. Then you have, let's see, well, two things are pushing upward or pulling upward. Its feet are on the floor, so there's presumably still a normal force due to the floor. And, let's see, this was 1, 2, 3, 4, 5 blocks, so that was 1, 2.5. I don't know if this is exactly the right. I don't think they're equal, but we'll just go with it. The other force that's up is the tension in the rope, which, since everything is in equilibrium, we can assume, static equilibrium, that we can assume that the tension is equal to mBg, the weight of the student that's just hanging there. All right, this guy right here. Meanwhile, B is straightforward. He's got his or her weight, mBg, and the tension in the string. And it's in equilibrium. Those two are equal. So the only thing I'm not sure about is that we don't know if these two are equal to each other, but certainly these two added together are going to equal this one, because, once again, static equilibrium. So if you have that diagram correct, this isn't that hard, because if you follow the process, which says I'm looking at student A, so let's do net force in two ways, MA, so mass A times acceleration, and net force equals, where do we go to get this statement? Free body diagram, ladies and gentlemen. All right, I go with all the upwards are going to be positives. So all the ups are going to be positives. We're going to go normal force plus tension minus MAG, the mass of person A times G. But they're not accelerating. Nobody's accelerating. So that's zero. The net force is zero. So I really have 0 equals normal force plus tension minus MAG. I'm going to leave it at this because I've already mentioned what I think this to be. And if I go through here, then I know tension, and I know the mass of person A, I know G. The only thing I'm missing is normal force. Come on. If you do the diagram, you do this, yeah, it's right there. Bleh, spits out. Now, maybe you didn't quite realize that, you got to have two forces here. He's not being supported by just, sorry, you can't see it. He's not being supported by just the tension. The floor is also lifting up on him. I did a demonstration like this in class, where I pull up on something a little bit, and you'll notice that the normal force goes down because the tension is now doing some of the work, or so to speak. Physics sense, not work, but all right. In this case, my only suggestion is, not really a suggestion, you're going to look at the force on dude B here, but in this case, if he's going to accelerate upward, the tension has to be more than his weight. So what you do is figure out what that tension is, but you're going to need that here because that's now going to be the tension that is on A during that period of time, and that tension is going to be a little higher, and the question is it high enough, down here, is it high enough to lift him off the ground? And then, I don't think it's going to be, and then this last one, you're like, oh, well, what does acceleration have to be? So then you work that same problem backwards. But free body diagram, net force two different ways. The key is getting your diagram right. If you do, this should all fall apart. It should all just fall out in your lap. All right, that's it.